Hey guys, in this video we're going to talk about 9.2 geometric series. So last time we looked at sequences, and sequences were just lists of numbers that followed a general rule. So for example, we could have the sequence 1, 8, 15, 22, 29, ... We could also have a sequence -8, 2, -1/2, -1/8, and it looks like the rule there is division by 4, right? Okay, so those are two examples of sequences. In this lecture, we're going to talk about series, and basically the only difference between a sequence and a series is that we're adding all of the numbers in a sequence. That's what a series is. So some examples. The first example we have is 1 plus 8 plus 15 plus 22 plus 29, ... etc. So here, we're separating with an addition sign instead of a comma. So this is also an example of a series. And even if you see minus signs, you can think of it as addition, because this is the same thing as -8 plus 2, and then we have plus -1/2, right? That's our next term, plus 1/8, and the pattern continues. Okay, so those are series. So series are separated by addition signs. Sequences are just separated, the numbers are separated by commas. Okay, so let's do some examples where we have to figure out if it's a sequence or a series. So the first one, we have numbers, right? 6 squared, 4 squared, 2 squared, 8 squared, and they're all separated by plus signs. So this is a series. And the next one, we have the numbers are not separated by plus signs. We're actually separating by commas, so this is a sequence. Here we have a series. Again, with the minus, you can think of this part right here as 1 plus -2, right? It's the same thing as 1 minus 2. And same thing right here. This guy is 3 plus -4, and so forth. So that's a series. And here we also have a series. We're not sure what the terms are. We have S1, S2, S3, but nevertheless, we're still separated by plus and minus signs. So this is a series. So we're going to talk about a specific type of series today, and that's called a geometric series. And the basic definition is that a geometric series is one in which each term is a constant multiple of the one before. We call the first term in the series A, and we call the common ratio between terms x. And we're going to do a bunch of examples with this. So a finite geometric series has the form a plus ax squared plus blah, 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 all the way up to ax to the n minus 1. So a finite geometric series ends, whereas an infinite geometric series goes on forever, indicated by these 3 dots at the end. So we don't have an ending here. Okay, so is the series geometric? If yes, give a and x. So remember, a is the first term and x is the common ratio. Now, to see if it's geometric, you want to see, is there a common number that I multiply to get from one term to the next? That's what you're looking for here. That's what x is. So x is the common ratio, or common multiple if you like that better. So let's look at this first one. To get from -1 to 6, what do we have to multiply by? We have to multiply by -6, right? Okay, cool. To get from 6 to -36, what do we have to multiply by? -6 again, so times -6. To get from -36 to 216, well, again, we have to multiply by -6. So -6 is the common multiple between terms. So we have, and actually this is sequence, not a series. but this is a geometric sequence because we don't have plus or minus signs, but it's still the same concept. So our common multiple is -6 because that's what we're multiplying each previous term by to get the next. And our first term is going to be this first thing in the list, which is -1. All right, let's look at our next example. We have -1 to 1. What do I have to multiply by? I have to multiply by -1. To get from 1 to 4, though, we have to multiply by 4. So since we don't have a common multiple here, this is not geometric. And we can just stop. All of those all the multiples have to be the same. Okay? Let's look at the next one. -2 to -4, we have to multiply by 2. -4 to -8, again, multiply by 2. -8 to -16, again by 2. So yes, this is geometric because the common multiple is 2. So x is going to be 2. That's our common multiple. And our first term here in the list is -2. So a is equal to -2. All right, so those are some examples of sequences. The number 1 and 3 were geometric sequences, and number 2 was not a geometric sequence. Okay, let's do some more examples that are a little bit more involved. Okay, so we're doing the same thing. We're looking from term to term. These are series because they're separated by plus and minus signs. And we want to see, do I have a common ratio x? Well, to get from 2 to 1, I had better multiply by 1/2. Again, to get to 1 to 1/2, I'm looking at this second one, 1 to 1/2. Again, I multiplied by 1/2. Again, I multiply by 1/2 to get from 1/2 to 1/4. From 1/4 to 1/8, again, I have to multiply by 1/2. So yes, this is geometric. And my x, my common multiple, is going to be 1/2. I have to multiply each previous term by 1/2 to get to the next. My first term in the series is going to be 2, as we can see there. So there it is. Okay, let's look at the next one. So I'm going from 5 to -10. I have to multiply by a -2. From -10 to +20, I have to multiply by a -2 times -2 to get from 20 to -40, and again times -2 to get from -40 to +80. So yes, this is geometric, and our common multiple, our common ratio, whatever you like better, is -2. Meanwhile, our first term is going to be 5, as we can see that's our first number in our series there. Okay, let's look at number 3. So here we're going from 1 to x. We better multiply by x. That's a weird, actually maybe I'll do the dot for times. Maybe that'll look better. Times x. Okay. Here, x to 2x squared, I had better multiply by 2x, right? 2x times x is going to give me 2x squared, but these are not the same. So right off the bat, you can say not geometric. We don't have a common ratio here. Okay. Excuse me. So that's not geometric because these two numbers right off the bat are not the same. Okay. Let's go to the next one. So here we have to multiply by -y squared. So 1 times -y squared is going to give us -y squared, which is the next term. And the next one, -y squared times what is y to the 4th? Well, that's -y squared as well. What times y to the 4th is -y to the 6th? That's -y squared. All right. So our common multiple here is -y squared. That's what we have to multiply each previous term by to get the next. And our first term in our series is the first number, which is 1. Okay. All right, let's look at this last one. All right, so z squared times what is -z to the 4th? That's going to be -z squared. Okay. -z to the 4th times what is -z to the 8th? Okay, be careful here. Remember our exponent laws. So this is going to give us negative z to the fourth, right? Because let's work this out. So if we're trying to see negative z to the fourth times negative z to the fourth. Well, remember with exponents, I keep the base and add the exponents. So I'm keeping the z. Negative 1 times negative 1 is going to give us positive z as my base. And then if I add the exponents, I get z to the eighth, right? Okay, so we can see here that since these numbers are not the same multiple, we can conclude that this is not geometric. Not geometric. All right. Okay, so I am going to give you an explicit formula for finding the sum of a finite geometric series. So we're interested in adding all of these numbers up, but if we were to take, let's say, the series 1 plus 2 plus 3 plus all the way up to 100, and we wanted to add up all these numbers, that would take a really long time and would be super tedious. So what we're going to do instead is we're going to derive a formula so that we can have a general formula for any finite geometric series. And actually, this isn't even geometric, but it's a series. So, okay, so that's what we're going to do. So the first thing we're going to do is we're going to just look at the general form of the sum of a finite geometric series. So here we have our first term, then we have our second term, which is our first term times our common multiple, and then our third term all the way up till our last term, a times x to the n minus 1. And by the way, n, let me write this right here. So n is how many terms you're adding up in your series. That's what n means, okay? So I'm going to do a little, some little manipulations here. And the first thing I'm going to do is I'm going to multiply both sides of this equation by x. So this is just a general finite sum of a geometric series, okay? That's what we have here. So if I multiply both sides by x, let's see what that is going to give us. So if I distribute that x in there, I get ax plus ax squared plus ax cubed plus dot dot dot. What happens when I multiply x times a to the x n minus 1? Well, remember, we have the same base x. The a can come in the front, and I keep the base and I add the exponent. So 1 plus n minus 1 is just going to give us a x to the n. Okay? All right, so that's where we're at so far. Now what I'm going to do is so this is x times Sn. What I'm going to do at this point is I'm going to subtract Sn minus xSn. So I have Sn minus xSn. So keep in mind, S sub n is right up here. X times S sub n is right here. Okay? So this is going to be a plus ax squared plus dot 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 plus ax to the n minus 1, that's S sub n, minus, and then in parentheses, what I just found here. Okay, so what's going to happen is we're going to have a lot of things cancel out. The only thing that we're not going to have cancel out is the a in the front, because you don't see a minus a here. So the a is going to stay. Ax is going to cancel. Can you see that? And so is ax squared. Can you see that? And so forth. The only other thing left that doesn't have a partner is the ax to the n. So that's the only thing left that's not going to get canceled. So this is going to give us minus ax to the n when we distribute this minus sign right there. Okay, so at this point, what I can do is I can factor out an s sub n right here. And what I'm left with is 1 minus x. Then over here, I can factor out an a. And I'm left with 1 minus x raised to the n. And finally, if I divide both sides by 1 minus x, I get a formula for the sum of a finite geometric series. I get a times 1 minus x to the n all over 1 minus x. So this is how we derive the sum of a finite geometric series, where a is the first term in our series, and x, so actually maybe I'll write this out to the side. So a is the first term in our series, x is the common multiple, and n is number of terms we're adding up. Okay, so that's our formula. And here it is again. Okay, so let's do some examples with this. We're going to say how many terms are in the finite geometric series and find its sum. So first of all, we can look at the pattern here and see that, you know, our common ratio, what all of these terms have in common is a 0.1. Right, this is 0.1 to the first, 0.1 to the second, 0.1 to the 10th. So how many terms do I have here? Well, it's pretty easy to see that we have 10 terms. So n is equal to 10. And what is our first term going to be? Well, our first term is this guy, this chunk, 2 times 0.1. And I can actually just leave it like that for now if I want. Now, what's the common ratio? Well, what do I have to multiply one thing to get to the next thing? Well, it's pretty clear I have to multiply by 0.1, right, to get to the next thing. So that is my x. X is 0.1. And now all I have to do is plug the stuff into my formula. So we have our formula. Our sum is going to be a times 1 minus x to the n all over 1 minus x. And if I sub in these values into my formula right here, what I'm going to get is the following. I'm going to get the sum is 2 times 0.1, that's a, times 1 minus 0.1 to the 10, so that's 1 minus x to the n, all divided by 1 minus x. Okay, and when you put this in your calculator, you should get that the sum is, let's see, 0.222. That is our sum. Okay, let me erase some of this stuff, make more room. 0.222 is our answer here. This is our answer for the first one. Okay, let's look at number 2. So first of all, our first term we can see is obviously 8. Okay, so let's see. Actually, let's write this down here. Okay, so we start off with whole numbers, right? And then we can see that we're like going to fractions all the way up to 1 over 2 to the 10. So the idea is to make the other numbers have a denominator of 2 to the something because we want to like keep the pattern going, you know? So how can I write 8 as a power of 2 with a denominator? Think about that. How can I write 8 with a power of 2 and a denominator? Well, 8 is 2 to the 3. So if I want to write it with a denominator, 8 is the same thing as 1 over 2 to the negative 3, right? Properties of exponents tells me that I can move the negative exponent to the top and make it positive. So this is the same thing as 2 to the 3. Okay, so 8 is 1 over 2 to the negative 3. That's the key observation here. So instead of writing 8, I can write 1 over 2 to the negative 3, comma, and then 4, same idea. It's 1 over 2 to the negative 2. 2 is 1 over 2 to the negative 1. 1 is 1 over 2 to the 0. 1/2 is 1 over 2 to the first, and I think you guys can see where this is going, all the way up to 2 to the 10th. So our common ratio is going to be 1/2, right? We can see that. I mean, we don't even have to look at the first two terms. Like, if it makes it easier, it tells us it's geometric. So we know for sure that the common ratio between any two terms is going to be the same. So 1 times what is a half? Well, that's a half, right? So we can, and 8 times 4. 8 times what is 4? That's a half. So our common ratio here is a half. And the question now is, what is n? So how many terms are we adding up? Well, okay, so we're adding up, this is 8. So this is 8. Let me just write this down. 4, 2, 1, 1/2. Okay. So how many terms do we have? We have 1, 2, 3, 4, and then 1. So we have 1, 2, 3, 4, and then we have 1 over 2 to the first all the way up to 1 over 2 to the 10th. So how many terms is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have 10 plus 4 is going to give us a total. So this is my first 4. And then I have 10 from 1 over 2 to the first, 1 to 1 over 2 to the 10th. So this is 10. So 10 plus 4 is 14 terms. Okay? Now what we can do is we can plug this stuff into our formula that I have written up here. Okay, so I have S sub n is equal to A, which is 8, times 1 minus a half to the 14. And this is all going to be divided by 1 minus a half. And when you put this in your calculator, you should get 15.999. And that is our answer here. Okay, looking at the next one, we have A is equal to 2 times 0.14 to the 5th. Our common ratio, would I have to multiply the previous term to get the next one? Well, that's obviously 0.14. And my n, so this is my first term, second term, and I'm going all the way up to 12. So 5, 6, 7, 8, 9, 10, 11, 12, that's 8 terms. Okay, so putting this in my formula, I have S sub 8 is A times 1 minus 0.14 to the 8, all divided by 1 minus 0.14. And this is going to give us approximately 0.000125. So that is going to be our sum. So the next thing we're going to look at is the sums of infinite geometric series. So far, we've just taken the sum of finite geometric series, so series that have an end. But the idea here is we want to first consider the partial sums. So that's just the finite sum. So like, for example, if I have, let's say I have 2 for 6, well, actually, let's say I have 2, 4, 8, 16, ... And I want to first consider the partial sums. So partial sums is basically, how many terms you're summing up. So like, for instance, S sub 1 would just be 2. S sub 2 would be summing up the first 2. So 2 and 4 is going to be 6. S sub 3, we sum up 2, 4, and 8. And that's going to be, let's see, 12 and 2 is 14, and so forth. So we're going to look at the partial sums. And what we're going to do with these infinite series is we're going to take n going to infinity, right? We're going to see what the sum is as n goes to infinity. So the partial sums of the first n terms in a geometric series is going to be represented by this formula, right? So, S sub 3 is going to be the first 3 terms in a series added up. And the question is, what is going to happen to the sum as n goes to infinity? So here we're talking about an infinite geometric series. And let's just look at the different cases. The first case is if our common multiple, the absolute value of the common multiple is less than 1. Well, then what happens? Well, let's do a concrete example here. So let's say that we have the series 1/2 plus a 4th plus an 8th plus ... So this is an infinite series. And here, my x is going to be a half, because that's what I have to multiply each term by to get the next. And therefore, the absolute value of a half is less than 1, right? So this rule is going to apply. But let's see why it actually works. So let's see why when we sum up this infinite series, we get this formula right here. This is actually going to be what our formula is for the sum. Why does this work? Well, let's look. So first of all, we know that the partial sums are going to be a times 1 minus x to the n over 1 minus x. But this time, we're looking to see what happens as the partial sums go to infinity. So the limit as n goes to infinity of a times 1 minus x to the n over 1 minus x. Well, let's look at our specific example right here. Here, x is 1/2 and a is also 1/2. So if we plug this stuff in, we have the limit as n goes to infinity of 1/2 times 1 minus a half to the n all over 1 minus a half. And let's go ahead and simplify this as much as we can. So we have limit as n goes to infinity of a half times, well, a half to the n is just going to be 1 to the n over 2 to the n. 1 to the n is simply going to be 1 for any n. So I can just actually make this 1 minus 1 over 2 to the n. So let's do that. Over 1 minus a half is just a half. And these cancel out. So I'm left with the limit as n goes to infinity of 1 minus 1 over 2 to the n. And we know what happens here. When we plug in infinity for n, we get 1 minus 1 over 2 to the infinity. And this guy, as the bottom gets huge, this thing goes to 0. 1 minus 0 is 1, right? So let's verify that this is indeed our sum with the formula that I circled right here. So again, this applies when the absolute value of x is less than 1. Well, here, again, a is 1/2, so our formula says infinite sum is equal to a over 1 minus x. In our case, a is 1/2, so we have 1/2 over 1 minus 1/2, because that's what x is again. And we get 1/2 over 1/2, which is 1. So that checks out. All right, so we can always use this formula right here when the absolute value of x is less than 1. So that's case 1. In case 2, if the absolute value of x is greater than 1, then what's going to happen is that the partial sums are going to oscillate between a positive and a negative value. Or if x is positive, if x is larger than 1, then the series is going to diverge. And let's see why that is. I'll just look at the case when the absolute value of x is greater than 1 and x is positive. Let's look at that case. Just so you guys see where this stuff is coming from. I just want to make sure that, you have some kind of like intuition about this. So let's clear off this. Okay, so this is case 2. The absolute value of x is bigger than 1. Well, let's consider, what could we consider? Well, let's just consider so this is an example of case 2. We could have 2 plus 4 plus 8 plus 16. So here, x is going to be 2, right? And of course, the absolute value of 2 is bigger than 1, so this thing should diverge. Let's see why. So again, we're taking the limit as n goes to infinity of the partial sums. So we have a times 1 minus x to the n over 1 minus x. And in this case, x is 2 and a is also 2. This is the first term. So we have limit as n goes to infinity of a, which is 2 times 1 minus 2 to the n over 1 minus 2. Okay? So simplifying this even more, we get limit as n goes to infinity of 2 times 1 minus 2 to the n all over negative 1. Okay, so this is just going to give us a negative 2 in the front. Negative 2 in the front. And if I distribute this guy, we get negative 2 plus, plus 2 times 2 to the n, right? And this becomes, I'm just simplifying this as much as I can, really. This becomes negative 2 plus 2 to the first times 2 to the n is 2 to the n plus 1. So so we can see what's happening here, right? What's happening as n goes to infinity? Well, we have negative 2 plus 2 to the infinity plus 1, which of course is just infinity. And 2 to the infinity is just a huge number that grows without bound. So we can see here that this thing is going to diverge because of this portion right here. 2 to the infinity is infinity. Okay, so let's do some examples. Now here I have the formula written for you if the absolute value of x is less than 1. If the absolute value of x is greater than 1, as I mentioned, the sum is going to diverge. So here we go. For the series shown, find the first 4 partial sums, and then find the sum of the infinite series. So first of all, what is our x? What is our a? Well, in this case, the first term is 1, so a is 1. And we can see that, what do I have to multiply to get from 1 to the next? That's going to be a half. So x is 1/2. And since the absolute value of x is equal to 1/2, and that's less than 1, we know that the formula here should be this guy, a over 1 minus x. So this is going to be this, which is going to be 1 over 1 minus 1/2. And this is just going to be 1 over 1/2, which is 2. So the sum of this infinite series should be 2. Now let's look at the partial sums. So the first sum right here, well, actually, let me write my formula up here. We have the partial sum is going to be a times 1 minus x to the n all over 1 minus x. Therefore, s sub 1 is going to be 1 times 1 minus 1/2 to the n. How many terms are we adding up? Just 1 over 1 minus x. And when I simplify this, this is going to give us, let's see. This is going to give us 1, which makes sense because that's the sum of just the first number here. Okay, so s sub 2 is going to be 1 times 1 minus 1/2 squared over 1 minus 1/2. So that's going to give us 3 over 2. S sub 3 is going to give us 7/4. And s sub 4 is going to give us, let's see, s sub 4 is going to give us 15 over 8. So you can see here, as s gets bigger and bigger, what's happening to the sums. Well, 7 over 4 is 1.75, right? And 15 over 8 is 1.875. And so what we're expecting here is as n gets larger and larger and larger, let's write this down. As n gets larger, the sum appears to get closer to 2, which makes sense. That's what we got right up here. We got that our sum was equal to 2. All right, let's do another example. So here we can see that our first term is 1 in our series, and we can see that the common ratio is 2. So x is equal to 2. Absolute value of 2 is bigger than 1, so we know right off the bat this thing is going to diverge. Okay, so we can't compute the sum. Now, let's go ahead and find the first 4 partial terms. So s sub 1 is going to be 1 times 1 minus 2 to the 1 all over 1 minus 2, and that's going to give us 1. As expected, s sub 2, well, really I could use the formula or I could just add the numbers up. I'm going to just add the numbers up, but you can use the formula if you want. S sub 2 is going to give us 3, right? The sum of the first 2 terms here. The sum of the first 3 terms is going to be 1 plus 2 plus 4. Again, you can use the formula if you want, but I'm being lazy here. So this is going to give us 7. S sub 4 is the sum of the first 4 terms, 1 plus 2 plus 4 plus 8. So that's going to give us 7 and 8 is going to give us 15. And so what can we notice here? Well, what we notice is as n gets bigger, the sum is going to get bigger without bound. So we can't compute the sum because this thing is going to diverge off to infinity. Okay, so we're going to find the sum of the infinite geometric series. So first of all, we can see that our first term is a, which is 6. And our common ratio, well, 6 times what is -2? That's going to be -1/3. Same thing here, -2 times what is +2/3. That's going to be -1/3. So our common ratio is going to be -1/3, common multiple if you like that better. And it turns out that the absolute value of -1/3 is equal to 1/3, which is less than 1, which means that we're going to use the sum formula. The sum is equal to a over 1 minus x. All right, so our sum in this case is going to be 6 over 1 minus -1/3. So this is 6 over 1 plus 1/3. So 6 over 4/3. And let's see what this comes out to be. So this is going to be 4.5. So this is our sum. All right, it says use the properties of geometric series to find the sum of the series. For which value of z does the series converge for? Okay, so first of all, let's figure out what a is and what our common ratio is. Well, a is clearly 1. Now our common ratio, 1 times what is z over 4? That better be z over 4, right? So times z over 4. And again, you can see if I multiply z over 4 times z over 4, I get z squared over 16. Okay, so that is our common ratio. So let's write this. We have a equals 1. Common ratio is equal to z over 4. And using the sum formula, well, first of all, for which values of z does the series converge for? What we're going to do is we're going to say, well, it converges if the absolute value of z over 4, which is x, is less than 1, right? And so, and so in that case, what we have is we have the first option is z over 4 is positive, so z over 4 is less than 1. And then we have negative z over 4 is less than 1, right? Because we're in the absolute value. So this z over 4 could be positive or negative. Solving both sides for z by multiplying by 4, we get z is less than 4 right here. And on the other hand, if we multiply both sides by -4, we have to switch the inequality sign because I'm multiplying by a negative. So these are the values for which z is going to converge for. Z is going to be greater than -4, but less than 4. So this is the values for which z converges. And assuming that we have a z between -4 and 4, we can go ahead and use our sum formula. So the sum is going to be a over 1 minus x. So in this case, we have 1 over 1 minus z over 4. So this is going to be our answer here for our sum. Okay, let's go ahead and do the next one. This is number 16. So we have 3 plus x squared plus x to the third plus dot dot dot. Well, first of all, you should notice that, 3 times what is x? 3 times what? 3 times what is x? Well, if I divide both sides by 3, that's going to be x over 3. So this is times x over 3. But here, I'm multiplying by x. X times what is x squared? That's x. So already, off the bat, we don't have a common ratio right there. But it seems that the pattern continues just after that first piece. So x squared times what is x to the third? That's going to be times x. And we're going to assume that pattern continues. So the geometric series doesn't start at 3. It starts, this is where geometric series starts here. Not with the 3. So in our case, the geometric series, since it starts at x, our first term is going to be x. And our common ratio is also going to be x. So our sum, if it converges, which we're assuming it will for some values, our sum is going to be a over 1 minus x. But we also have to, so that's the sum of just this part, the geometric series. But we also have to add on the 3, right? That's also part of our sum. Even though it's not part of the geometric series, it's still part of the sum. So this is our sum, and for what values of x does the series converge? Well, remember, we want the absolute value of x to be less than 1 to converge. And so what we have here is we have x is less than 1, or we have negative x is less than 1. So here x is less than 1, that's pretty clear. If I divide both sides by negative 1, the sign has to flip. All right, so we have x is smushed between negative 1 and 1. So these are the values for which the series converges. X is between negative 1 and 1. Okay, so let's talk about series notation. So we have this big thing that we call sigma. And basically what it tells us is where to start summing and where to stop summing. So, and then this, whatever is like next to sigma is our function. So 2 to the n, from n equals 0 to n equals 3, means that we're going to first plug in 0 in for n. That's our first term. Then we're going to add up 2 to the 1, 2 to the 2, all the way up until the end point, which is 2 to the 3. So that's what that means. On the other hand, we could have an infinite series like this where we're starting at n equals 0, so 2 to the 0 plus, okay, then we go to the next number, n to the 1, plus, and actually this kind of has an error right here. This should be 2 to the 0 plus 2 to the first plus 2 squared all the way up forever, right? Because this infinity means that we don't have a bound. We're just going to keep adding up our numbers forever. So that's what that means. So let's do some examples. Is the geometric series convergent or divergent? Well, let's write out what this actually means. So we're starting at n equals 1. So I'm going to go ahead and plug in 1 first for n. Anywhere I see an n, I'm going to plug in 1. So I have 2 times 2 to the 1 times 3 to the 1 minus 1. Okay, so that's our first term in our series. And if I simplify this, if I simplify this is just going to be 2 squared times 3 to the 0, which is going to be 4 times 1, which is 4. So that's our first term in the series. Our second term in the series is when n equals 2. So when n equals 2, I simply plug in 2 anywhere I see an n. And I simplify. So this is 2 to the 4th times 3 to the negative 1, which is going to be 16 over 3. Okay? So basically, all we really need are our first two terms here. We have 4 is our first one, plus 16 over 3 plus dot dot dot. But we can say everything we need to know just based on those first two terms in our series. And that is whether it's convergent or divergent depends on whether or not the absolute value of the common multiple is less than 1. So the common multiple here, 4 times what is 16 over 3? Well, that had better be 4/3, right? So our common multiple is 4/3, and the absolute value of 4/3 is greater than 1, right? And that tells me that we can't compute the sum. That tells me that the sum diverges. Okay, so that's our answer. The sum is divergent. Okay, let's determine whether or not this series diverges. So again, I'm just going to start by writing the first few terms here. So first of all, I have 1 over square root of n. If n is equal to 1, I have 1 over the square root of 1, which is going to be 1. So that's our first term. The second one is 1 over the square root of 2. So that's just 1 over square root of 2. The third one is 1 over the square root of 3, which is just 1 over the square root of 3. But the problem is that when we, if we're multiplying by a common ratio here, we have to multiply by 1 over the square root of 2. Is it true that 1 over square root of 2 times 1 over square root of 2 is going to give us 1 over square root of 3? No, right? So first of all, we're looking to see if it's geometric first. This problem is just different from this one because it already tells us here that's geometric. So we were working under the assumption that this was geometric. But here it's saying, is it geometric first? And the answer is no. No, not geometric because we don't have a common multiple. If we did, then, we would have the multiple 1 over square root of 2. 1 over square root of 2 times 1 over square root of 2 is simply 1 over 2, which is not 1 over square root of 3. So this is not geometric. We cannot compute the sum with the tools that we have right now. All right, let's do some examples. It says determine the sum of the geometric series. So we're working under the assumption that it's geometric, that it has a common ratio, and determine whether or not it is convergent. Okay, so let's look at this first one. What we can do is we can first write some terms out and expand. So the first term is going to be 6 times 0.9, and then we're starting at n equals 1. So the first one we're going to plug in for n is 1. So that's our first one, plus our second one, which is 6 times 0.9, and instead of n, we're putting 2 because it's the second one we're adding up. And that's all we need because we know it's geometric, so whatever the ratio is for the first two terms, it's going to be the ratio for the other ones. So what I can do is I can simplify this, and 6 times 0.9 to the 0 is simply 6 times 1. Anything to the 0 power is 1. So this is just 6. And then the next one is 6 times 0.9. And the third one is going to be 6 times 0.9 to the second power and so forth. So what's the common ratio here? The common ratio, 6 times what is 6 times 0.9? Well, that has to be 0.9, right? So x equals 0.9. The absolute value of 0.9 is 0.9, which is less than 1. So we can use our sum formula, a over 1 minus x. So the sum is going to be a. Our first term is 6. So that's a over 1 minus an x is 0.9. So this is going to give us 60. That is the answer for number 1. That's our sum. So it's convergent, and it converges to 60. Let's write that down. There we go. All right, let's look at number 2. So again, we're told it's geometric, so let's write out the first two terms here. If we plug in n equals 1 into this guy, anywhere we see an n, we get negative 3 to the 1 minus 1 divided by 4 to the 1. And that's going to be negative 3 to the 0 over 4. Anything to the 0 is 1, so our first term is 1 over 4. So that's our first term. And that's a, actually. Our second term is going to be when n equals 2. So negative 3 to the 2 minus 1 over 4 to the 2. This is going to give us negative 3 to the first, which is just negative 3 over 16. So that's our second term. So 1/4 times what is equal to negative 3 over 16? Well, it has to be negative 3/4, right? So x is equal to negative 3/4. Right? If we multiply negative 3/4 by 1/4, we simply get this. Okay, so let's clean this up a little bit. So we know our first term is 1/4, so I'm going to leave that. Now, the absolute value of negative 3/4 is less than 1. So this converges. So the absolute value of negative 3/4, which is x, is less than 1. So this converges. And we can figure out what it converges to with our sum formula. So our sum formula is a over 1 minus x. 1 plus 3/4 is 7/4. So this is going to give us 1/4 times 4 over 7 is 1 over 7. So this is our answer here. 1 over 7 is the sum. Okay, let's look at number 3. So number 3, let's write the first couple of terms out. We know it's geometric. So the first term is when n equals 0. So if I plug in 0 anywhere I see an n, my first term, which is a, is going to be pi to the 0 over 3 to the 0 plus 1, which is simply pi to the 0 is 1 over 3. So a is 1 over 3. Now for my second term, I'm going up 1, so I'm going up to n equals 1. So I have pi to the 1 over 3 to the 1 plus 1, which is simply pi over 9. All right. So what's the common ratio? 1/3 times what is pi over 9? Well, that has to be pi over 3. So x is equal to pi over 3. Now, the absolute value of pi over 3, if you put pi over 3 in the calculator, it's a number bigger than 1. So this is bigger than 1, which means that this sum diverges. So there is no sum here, it diverges.